Alrighty, we are in chapter 12 right now. As you know, we did the 2 sections of chapter 10 because they had to do with circles as well. And now we're jumping into chapter 12. So today's lesson is called tangents. So the start thinking part says the following are all examples of tangents. Look at the figures and come up with a definition of a tangent. Let me go ahead and show you some things that are not tangents. Okay, this is not going to be a tangent right here. This is not going to be a tangent right here. These are all going to be tangents. This is not a tangent up here as well, if you have the line all the way up there. So people at home, I want you to take a second, try to come up with a definition of a tangent, and people in class, go ahead and come up with your own little definition of what a tangent is and how it relates to a circle. All right, hopefully people at home had a chance to go over and think up a definition. So in class, what did you guys get? Student right here. What did you guys get? A line that does what? It doesn't cut it in half. It's better to talk about what it does do rather than what it doesn't do, because it doesn't do a lot of things. How many times? Fantastic. Okay, what a tangent line is a line that intersects a curve exactly once. Now, what we are talking about in our class, because we've been working with circles, is tangent to a circle. So let me show you an example when you would have a circle that has a tangent line. If you're riding a bicycle, how many times does the wheel touch the actual ground? Once. So those wheels are going to be tangent to the ground. Now let me show you, just give you a glimpse of what you're going to be using tangents for in the future, especially you kiddos that are going to be going to pre-calc and calc. So if you look at a line, you learned about lines in Algebra 1. If you look at the rate of change between here and here, it has a certain rise and it has a certain run, aka slope. If you look at the slope up here, what do you notice about the slope up here versus the slope down here? It's the same. What about the slope from this point to this point? This rise and this run, if you went over and simplified that. What do you notice about the steepness of the line for that whole thing? It is exactly the same. Now let me show you how you're going to use this a tangent line in like pre-calc and calc. If we look at this curve right here, what do you notice about the steepness of the curve? Is it super steep or not steep at all? No, right, you're telling me that this right here is steep? So in like an algebra class, when you're just getting into math, they know you can't handle going over and seeing things that change too much. You're looking at a line that has the same exact steepness throughout. When you get to calc and pre-calc, what do you notice about the slope down here? It's not steep at all, right? What about the steepness right there? Well, it's starting to get steep, it's getting steeper, and so on. So what calc does is rather than going over and picking a random point and another random point and figuring out the slope between those points, they start pushing these points closer and closer to one another. So maybe the point will be here and here, and then they keep pushing them closer and closer. And calc is going to go over and push those points so that they're infinitely close to one another. If I drew the line of the slope between the 2 points that are infinitely close, what type of line is that? That line is only intersecting the curve once. What do we call a line that intersects a curve exactly once? A tangent line. Like that's perfect. So what they will do is if you want to find the slope at exactly that point right there, you would find the slope of the tangent line. And the slope of the tangent line is going to give you that instantaneous right there, that exact slope at that exact point. Because if you go to a different point, it's going to have a different slope. And you're able to look at the different slopes on that curve by looking at the slope of the tangent line. Does anybody have any questions on that? Okay, so what a point of tangency is going to be is it is going to be the point a tangent intersects the curve. So this is the main thing that we learn in today's lesson. If you have a circle and you have a tangent line and then you make a radius going to that point of tangency, how does it look like the radius intersects the tangent line? Perpendicular. Fantastic. If a line is tangent to the circle, then it is perpendicular to the radius at the point of tangency. Well, we know perpendicular leads to right angles. Now let's figure out all the applications I'm going to be able to embed into this. Right angle we know is 90 degrees. So I'm going to be able to do something where you have to know that this is equal to 90 degrees. Right angles also make right triangles. What are some things we can do with right triangles? Anybody? You can do 30, 60, 90s. Fantastic. You can also do 45, 45, 90s. You can also do, what is the theorem that you need a right triangle for? Pythagorean theorem. You can also do, what's another thing that you need a right triangle for? Trig. What's another thing? Well, we can do HL. HL proofs need a right triangle. What's another thing? Well, we know all right angles are congruent, so we can use proofs that involve right angles. All of these things, since they are connected to a right angle, I can embed into the problem because we end up with right angles here. Anybody have any questions? All right, let's look at some practice problems here. So right here, we have this figure. It is a quad. And they tell you that this is 117 degrees. They want to know how many degrees that is. Anything in today's lesson that looks like a tangent is going to be a tangent. So is there anything else we can add into our diagram knowing that those things are tangents? Type of angles are these going to be over here? Right angles. They're going to be congruent angles that are both right. At this point, this is a four-sided figure. What is the sum of the interior angles of a four-sided figure? It is 360. So we know that 360 degrees is going to equal that 117 plus the two 90s together, which is 180, plus the x. And at this point, we can go over and someone with a calculator can do 360. It's 63. Great. So it's going to be 63 degrees left over. Does anybody have any questions on that? Okay, what I want you guys to do at home, go ahead and pause the video. I'd like you to try this second problem. People in class, go ahead and try the second problem. You are going to use the fact that this thing is a tangent. All right, hopefully the people at home actually worked through that problem like the kids in class did. They said that this was a 90-degree angle because it was a tangent. So since it's a triangle, it's going to be 180 degrees. You have 90 accounted for. You have another 38 accounted for. And you have the leftover angle. When you subtract everything away, you got x equals, would you guys say 52? 52 degrees. So this would be an example of how you can use tangents, just the angle being 90 degrees. Now on this one right here, this freaked kids out a little bit last period. It's only this that's 2, because a lot of kids said, hey, the hypotenuse can't be smaller than the other sides. So is there any other information I can draw into here, like information we can deduce from the numbers or the variables we already got? Yep. Great. Yep, the other radius is going to be 3, so this is going to be 5. So we basically have this triangle, and we can't do anything with just basic triangles, but since we know that's a tangent, this must be right. And you have a 3, an x, and a 5. Why do you say 4? Great. So a student class just said that that is the Pythagorean theorem, and beyond that, he realized that this is a Pythagorean triple. And the Pythagorean triple is 3, 4, 5, or any multiple, 5, 12, 13, or any multiple, 7, 24, 25, or any multiple. There's infinitely many more, but those are the ones that I memorize. So this would be a 4, Or if you didn't see that, you would have done the Pythagorean theorem and gotten the same thing. Does anybody have any questions on that? So the next one, we obviously have a right triangle again. So this is x, that's x plus 8, and this is 12. And once again, we have the sides of a triangle. I'm going to use the Pythagorean theorem here. I can't use trig because to solve for x because I don't have an angle. So I'm going to write this out as a squared plus b squared equals c squared. The stuff on the left is easy. That's just x squared plus 144. This over here, you are going to be tempted in Algebra 1, in Geometry, in Algebra 2, and in every class, you're always going to be tempted to just distribute this exponent. You're not allowed to do that. You actually have to write it out as x plus 8, x plus 8. And anybody, can you bring yourselves back to Algebra 1 and remember how you multiply a binomial times a binomial? No, it's the opposite of factoring. Foiling, great job. Awesome. So foiling means first times first, x squared, outer times outer, O, that is 8x, I, inner times inner, L, last times last, and that gives you 64. So you get x squared plus 16x plus 64. Now I get grumpy whenever I have a quadratic, because a quadratic usually results in you having to factor or do the quad formula. But I'm happy on this one because when you are solving using quad formula or factoring, either way, you are going to get one side to equal 0. So let's start going over and trying to get one side equal to 0. Let's say I subtracted this x squared so that I could get that side to equal 0. Now I'm happy because when I subtracted that x squared, the other one went away as well, and it no longer is a quadratic. That's not right. 64. 64 is over here. Oops. 64. Okay. And now it's just a basic equation. We can subtract 64 and just subtract 64. Someone tell me what it is. 80. 80 equals 16x. And when you divide by 16, what do you get? 80 divided by 16. 5. Great. Hey, guess what? Just like I like those Pythagorean triples, the other people like the Pythagorean triples as well. Take a look. When I put a 5 here and then I put a 5 in there, that becomes 13. What type of triangle is it? 5, 12, 13. The people who made this problem knew that 5, 12, 13 were nice numbers, so they went over and crafted the problem based on that Pythagorean triple. Anybody have any questions? Cool. Let's keep on cranking. All right, when we look at this, it says if a line is on a plane with a circle, it is, it's supposed to say it is, oh no, wait, I think and. There we go, put the word and in there, oops. If a line is on a plane with a circle and is perpendicular to the radius at its endpoint, then the line is a what? Well, we already learned that if it is a tangent, then it is perpendicular to the radius. What do you think is true if you have some line that is perpendicular to the radius? Then that line will be a what? Tangent. Fantastic. The connection here is we learned the Pythagorean theorem that says if you have a right triangle, then a squared plus b squared equals c squared. And then we learned the converse, which says if a squared plus b squared equals c squared, then the triangle is right. So this was the theorem, and this was the converse. It's kind of the same thing. The new one says, hey, if it's a tangent, then these things are perpendicular. And then the other one said, hey, if these things are perpendicular, then it's a tangent. So when you're looking at something like this and you're trying to figure out, is this thing a tangent? You just have to first find out if this is a right angle, and if it's right, then it's perpendicular, and if it's perpendicular, then it's a tangent. So the best way to find out if that's a right angle is just see, does a squared plus b squared, does that equal c squared? Does 7 squared plus 24 squared, does that equal 25 squared? And you let the math or the calculator do the math for you. So that's 49. I don't know what 24 squared is, but I do know this is 625. Did anybody do 24 squared? I don't have my calculator on me, so someone else is gonna have to do it. 24 times 24. 576. Okay, does 576 plus 49 give you 625? It does. So yes, since a squared plus b squared did equal c squared, then that is a right triangle, that is a right angle, those are perpendicular, so that is going to be a tangent. Does anybody have any questions on how to figure out if something is a tangent or not? None? Okay, the last theorem that we are going to look at is this one right here. This basically says that if you had a circle and you had a tangent and you had another tangent, how does it look like those two segments are related? This segment and this segment right here. They appear to be, what's that? Congruent. You are correct. They are congruent. So basically the rule is if you have a tangent, you have another tangent, and they intersect somewhere outside of the circle, then those are going to be congruent. Anybody have any questions on that? I like to do little proofs. Even if we're not going to do like a 2-column proof, let's just try to figure out why that is real quick. So I want to prove that that is congruent to that. We already know that these are right angles. We know that this is going to be a radius and that's a radius, so all radii are congruent. And then thinking back to your triangle proofs, what else do we have with these two triangles? Reflexive property. Okay, and if we have a leg, a right triangle, and a hypotenuse, that would be the two triangles are congruent by HL, therefore their parts are congruent by CPCTC. So even though I'm not doing a 2-column proof, the reason I taught you guys proofs was so that you could think through something and be like, those look congruent. Are they actually? Well, this is based on math. Before we were just like, they look congruent. So we know that they have to be congruent by CPCTC, HL, and the whole little proof that we just did. All radii are congruent on the circle. Then we have the right angles and we have the reflexive property. So what must be true about this and this if those are both tangents? They must be congruent. Fantastic. So we can say 6x plus 1 equals 2x plus 17. And then we just solve it. I'm going to subtract 2x, subtract 2x, that gives us 4x, minus 1, that gives me 16. And what do we get for our answer? 4. Does anybody have any questions on that? So for that problem, we just had a tangent and a tangent, and we're only looking at this. Technically, you can throw more tangents in there. So what you'll end up with is an inscribed circle. An inscribed circle is just going to be a circle that touches all sides once. Now let's see if you guys can dig deep into your memory. I forget what chapter this was, but it was probably like 5 chapters ago. If we have a triangle and we want to get the circle that's on the inside of the triangle touching all the sides, do we make perpendicular bisectors, angle bisectors, altitudes, or medians? Well, let's go ahead and do medians. It's not medians. The problem here is if I do medians, it's going to kind of look like it would be the right location, but it's not, because you can see this is closer to these sides than it is to this side over here. It is angle bisectors. Okay, so great job. You got all the answers. That's awesome. Okay, so if you do an angle bisector, you do an angle bisector, and you do an angle bisector, Good job on your memory. That would be the center of a circle that touches all of the sides. So let's go ahead and do these two problems and then do a quick proof. So if this was 15, then what does this have to be if they are tangents? That's 15. This has to be 15. If this is 8, what's the other one going to be? 8. If this is 10, then the other one's going to be 10. And technically, we could go over and figure out what the perimeter of this thing is. Does anybody have any questions on how we did that? Okay, before we do the proof together, here's problem number 2. I want you guys at home to pause the video. Try this problem. You're going to use logical reasoning to figure out what BC, AB, AF, and ED are. And people in class, go ahead and do that with your groups. We'll be back in just a moment. All right, hopefully people at home were working as hard as the kiddos in class. If this is 7, then that's going to be 7. If you have 16 and that's 7, that means this is 9, and that's got to be 9. And you're going to have a 2 and a 2. Once you fill that in, you can go back in and figure out what the values or the lengths of BC and so on are. BC is going to be 7, AB is going to be 9, AF is going to be 9, and ED is going to be 2. Does anybody have any questions on that? All right, we've got one last thing, and this is to pull up some proofs. I know we did proofs last semester, but most likely you're going to have some proofs on the final for this semester. Not many, not super hard, but just to make sure you remember it. So on here, we're trying to prove that these sides are going to be congruent. Think back to our days of proofs. How do you end a proof if you're trying to show an angle is congruent to an angle or a side is congruent to a side? CPCTC. Great. We know that if we're going to do CPCTC, we need to show a triangle is congruent to a triangle first. So our job now is to show these triangles are congruent. We already know that that's congruent to that. If this is a tangent, then those angles are going to be right. And we need one last piece to be able to show those triangles are congruent. Reflexive property. And now those right angles could have led to HL, or it could have led to SAS, AAS, or AAS. Now looking at this, you say it's what? SAS. Great. Okay, let's go ahead and put it all into a proof. Every once in a while, we do need to do a 2-column proof just to make sure we remember how to do this. Oh, yeah, that's what I meant. I wrote AAS twice. Oops. Okay, so on here we have BC is tangent to circle A at D. That's given. If it is a tangent, then we know that AD is going to be perpendicular to BC because tangents are perpendicular to radius. Now that we know that they are perpendicular, I can now say that the angles are right. Angle ADB and angle CDA are right. Def of perpendicular. So if we're ending with SAS, do we care that the angles are congruent, or do we want the triangles to be right? Does anybody remember for SAS? Well, for SAS, you have an A in it, and A's always mean the angles are congruent. So now we're going to say triangle ADB is congruent to triangle CDA because all rights are congruent. All right angles are congruent. What's that? Oh, we're not doing triangles. So when you do the triangles are right is when you're going to be leading to HL. And we're not going to HL, we're going to SAS. Okay, now what we can do is we can say that DB is congruent to DC, given. We know that AD is congruent to AD, reflexive. And now we can finally say that triangles are congruent. Triangle ADB is congruent to triangle ADC by SAS. And lastly, AB is congruent to AC by CP/CTC. I do want to finish the video just so that people aren't having to go much past 25 minutes. Does anybody have any questions about tangents? The main thing that we use with tangents are the fact that it intersects exactly once, like a bicycle tire touches exactly once. Later on, you're going to be using tangents to find instantaneous rates of change. And then the main thing here that we're using is the fact that the tangent is going to be perpendicular to the radius. All right, people at home, thanks for watching.